Let's now study about speed of a transverse wave on a stretched string. A transverse wave means a wave in which the particles would oscillate perpendicular to the direction of propagation of wave. Let's consider a case where we have a string attached to a wall where one end of the string is free. Suppose at the free end, if we give a small push like a jerk, then what happens is in the string a pulse is generated. The pulse moves like this. As time goes on, pulse keeps on moving forward. Pulse moves forward, moves like this. Now let's find out as to what would be the speed of this pulse or a wave in case of a stretched string. To understand this, let's look at the small part alone and magnify and see it like this. Let's assume that we are in the frame of reference of the pulse itself. In this case, we assume that the string is stretched like this. Take only a small part of the string as given here. Then we can assume that a small part of a string is like part of a bigger circle. So let's take a small portion of this string. But since we assume that this is part of a circle, it will have a center called as point C. Let's mark two extreme ends of the element taken. We consider a small element here given here. Let's draw a line which is passing center of this element. Let the angle made here be some theta. In this case, there will be tension which acts on the string, that is tension which acts tangential to this part as well as this part. So there will be tension acting this string because it is a stretched string. Let us call this tension as T and then T. Now to draw a straight line here, we put an axis here, then this T will have two components. This T is like this. We are putting one axis like this and one like this. This axis is towards the center. We can call this as y-axis, this as x-axis. This angle also made would be T. The angle made would be theta. This component would be T cos theta, and also this component would be T cos theta. And then the component towards the center would be T sin theta. So we have four components now. That is, one component is like this, which is T cos theta. The component which is like this, T cos theta. Both are same value. And then there will be one component which is T sin theta because of one tension. And also one more tension acts like this. It will be T sin theta. So there will be a component of T sin theta because of this tension as well as this tension. Therefore, the net force towards the center would be 2T sin theta, and this would be a restoring force because this force tries to restore the string to original configuration or original shape. Let's call restoring force as Fr, that is equal to 2T into sin theta. Let this length of this small element be called as dl. In this case, since the string is quite long, it is difficult to find the mass of any given region. So in this case, we define a term called as mu. This mu called as mass per unit length, which will be a constant for a given string. So let the mass of this be dm. Therefore, for the small element, the mass dm would be, it will be mu into length from this formula. So dm becomes mu into length, and let us call the length as dl as seen here. The mu into dl. This is what is the mass in this part. Now if we assume that this element is very small, then the angle theta made here and here would be small only. So for small angles, sin theta becomes same as theta itself. So for small angles, sin theta is same as theta itself. So from this arc element, this dl is arc element, and let the radius of the circle be r. For this arc element, we know that dl is equal to r to root theta, because recall that s is equal to r into theta. So here the arc element dl is equal to r into 2 theta, or 2 theta is equal to dl by. When we put it back here, then we say the restoring force is equal to 2t into theta. This for small is restoring force be 2t into theta would be dl by 2r, because from here theta would be dl by 2r. From this 2 gets cancelled, therefore the restoring force would be t into dl by. This is what is the restoring force. Now this restoring force would cause an centripetal. This is restoring force is the centripetal force which would cause particle or the wave to move. So we know that case of a centripetal force, acceleration, which is AC, is given as v square by r. This is the relationship between centripetal acceleration, velocity, and then radius. If we multiply mass on both sides, that gives us force. So dm into AC is equal to dm into v square by r, because you're trying to find out the velocity for that arc element only. This is called as restoring force. So if you compare these two equations, let's call this as 1, this as 2. From 1 and 2 you can say t into dl by r is dm into v square by. From here r gets cancelled, and also we know that dm is equal to mu into dl. Therefore you can say t into dl is equal to dm was mu into dl into v square. Again from here dl gets cancelled, therefore v square is equal to t by mu, or v is equal to the root of t by mu, where t is the tension in the string and mu is called as mass per unit length. This is the expression for velocity for transverse wave on a stretched string. The same expression can be obtained in much a simpler way by using method of dimensional analysis. You can try on your own and say this. So assume that velocity is proportional to some t power a u power b. Solve from here, and the constant which is taken to be k in this case, so k into t power a into u power b. Put the constant k is equal to 1, you get the same answer. This is a more simpler way of solving the same expression, and this is a more general or a more clinical way of solving it, because we know what the constant also here would be.